Weather briefing, 30 of May 2019. Well, I'm clearly overdressed in this picture. I have to change it some other time. But let's look at the weather. And here in Lisbon, it's predicted a sunny day, no clouds. The maximum temperature forecasted is around 36 degrees for today. So it's almost like summer has arrived a little bit earlier. So as for you all, as usual, we want to know where you are coming from, and if you can put there also the weather and the maximum temperature for today, it will be also pretty funny. Let's look. Yeah, so Poland, I think, Croatia, yeah, the British Isles, Spain. Latvia, I think. Okay, pretty scattered as usual. Oh, Serbia. Okay. Let's start the main part of this weather briefing. So I'll start by analyzing a little bit of this RGB Airmass. This is the image for the 6U2C of today. So I think it's well, we already know that this RGB can be used during day and night, so with no change in color interpretation during the whole year. And today I'll use this RGB mainly to determine the location of warm, dry air and some areas of subsidence, and also some frontal cloud systems, and namely the descending dry stratospheric air on the rear of its front. So if you can point out where do you think it's the warmer and or driest air mass in this RGB? It's an easy question, I think. Yes. Yes, of course. Yeah, mainly this part here, so which is affecting the Iberian Peninsula and Morocco, north of Africa. So let me just clear all notations. So if you look at more closely to the channels of this RGB, we can see that we have a red color in the two water vapor channels. Let me just point out here. So this is the red color with water vapor channels. The difference helps understand the difference in humidity between the mid layer associated with 7.3 and the higher layers of the troposphere associated with the 6.2. And so for this channel, small values means that there are mid-layer humidity and clouds, and higher values means there is high-level clouds, mainly when there's only high-level clouds, or it can also mean the high values can also mean dry upper levels. So when the two of them they are null. So for the green, we have for this green here. So we have a green color with two infrared channels, the 9.7 and the 10.8. This difference helps identify clouds on all of the troposphere and the height of the tropopause. mainly because of its ozone sensibility. So small values relate to ozone-rich troposphere, usually cold air masses or polar air masses, and higher values correlate to ozone-poor troposphere, so usually warm air masses and tropical air masses. The blue color is the only one channel, the water vapor 6.2, so small values are for dry upper layers, and when there is a moist upper layer, we should see some high values. So looking at this area, we can see that the blue has small values, so we have a dry upper layer. But is the rest of the troposphere really dry? I think if you look at the red channel, we have some small values, but because of the water vapor 6.2 is smaller than 7.3. But as we've seen before here, so with the blue, we have 6.2 that indicates that the higher levels are dry. So a mean value from the 7.3 can drop the value of this red channel, and the green as a mean value. So looking at look at the differences between these areas. You can see these areas here. Let me just point out these areas here, these here. These areas are of descending dry stratospheric air on the rear of this front. So we have here a cold front here, and we also have well, it used to be a cold front and then undulated, and now has some convection associated. So we look at if you look the difference between these two, between this area here and the other areas, we can see that green values lowers a bit here, and that indicates that a higher amount of ozone in the area, and that the mid-level humidity dropping compared to the warm air mass. So we have so that's the difference between these two green channels, and you can also see that in the red difference. So the blue between the two of them has no change. So both areas have a dry upper layer as expected. So within this warm area, there is I don't know if you can see, but there's a different spot in the middle of this warm area where we have the arrow pointing. Here we have just clear. Here we have a higher contribution of the 6.2, as you can see, and it only affects the blue color, and there's no effect in the red difference. So sometimes we have to be careful when we use this difference, this red difference, because not all the values of the water vapor can have an effect on the difference because of the algorithm that is used. So as you can see here, clearly the water vapor is different in both of them, but when we see the difference in the red, it doesn't change. This is mainly due to it's due to the algorithm used. So looking at the phenolitic situation, so we have high pressure system here in the Biscay Bay, extending to to the Eastern Europe, and we have a low here over Morocco, and this low here over near Italy, and these lows up here. So we have the warm front and and the cold front here. Looking at the water vapor, we can clearly see that that we have some darker areas here, where we point for the descending air before. Also here, but here, and so we have here you have the 500 hectopascal geopotential, so you can see clearly the low over the Adriatic, and here you have a high and the low over Morocco. So this configuration I'll show you a little bit later. That I'm talking mainly about the high over the Biscay Bay, and the low over Morocco has an impact mainly in the Iberian Peninsula. Just a quick look at the severe storms, RGB. So this RGB is mainly used for convection monitoring, and can only be used during daytime. So at 6 UTC, this part here is unusable. So the red color is equal to the Airmass RGB. We have a red color with the two water vapor channels. The green color is the difference between the 3.9 and 10.8 infrared channels, and they correlate to the size of the particles and temperature of the cloud tops. So it identifies opaque ice clouds with small values representing large particles, and or not a very cold cloud, and higher values representing small particles and or a very cold cloud. And the blue color differentiates between ice and water clouds. So ice has small values and water clouds have high values. So looking zooming here in this area, we can see that Austria, Slovakia, Hungary, and South Poland are under the influence of this weather pattern, and if we look at the red channel, indicates that we have high level clouds because of the high value. We look at the green as a mean value, and the blue it's more of a this value indicates more of a thick ice cloud. So we may be looking at the thick ice clouds, which may have large ice particles on top, and not very cold cloud top. Looking at the microphysics, 24-hour microphysics RGB. So as the name says, it's usable during the 24 hours. It mainly differentiates ice and water clouds and detects cirrus clouds. So the red differentiates between thin clouds and moist atmosphere. That's low levels for the red. And and differentiates between these thick clouds and moist atmosphere and thick clouds and dry atmosphere, and these ones are for higher values. As for the green, when we have no clouds, it differentiates. When we have clouds, it differentiates ice clouds with small values and water clouds with high values. And the blue differentiates from cold thick clouds and for small values and warmer thick clouds or warm land. So we can see here that this zone we can have thick clouds. This zone here we've seen before. We have thick ice clouds, and this is converges with the severe storms RGB. So only the green and blue channels looking at these areas, so the main Portugal and the desert and this area here, we only the green and blue channels give a clear signal. For the desert, for this part here, the desert, the blue indicates hot, so the green, although we need clouds to differentiate between ice and water clouds, in the desert the green value difference is high. So when this difference is high, we have in the desert, it indicates that it's desert sands. So, but to use the green cloud in a more usual way, we have to have the clouds so we can differentiate between ice and water clouds. But as you can see in the desert, it has a very clear signal. So in the Iberian Peninsula, the blue indicates hot. The green, as we have no clouds and no desert, it can be overlooked, and the red is more to the dry side. For the frontal systems, mainly this one and this one, we have the green indicates ice values, so we have a small value, and the blue indicates cold thick clouds for these areas. So zooming over the Iberian Peninsula, we can see the difference in the 24-hour microphysics RGB between the 6 UTC of today and 15 UTC of yesterday. If you look at the colors, they are different, and where can you see the difference in the combination of the RGB? So as the land is warmer, in the blue 10.8, as you can see here, for the 15 UTC. So it has this channel, the blue channel, has a higher value, and so it affects this channel, the blue channel, and also the other channels, because 10.8 is present in the 3 channels, because it's evolved, and so the colors also change, and you can see the difference, just to show the difference between looking at this RGB during the beginning of the day and at almost top of the day. So I used this image from yesterday just to see the von Karman vortex effect developed at the lee of the Madeira Islands here and Canary Islands, mainly this part here. So we had these stratos or stratocumulus, and we had an inversion mainly in Madeira Islands, and the winds are persistent with a northeast winds, and since these are mountainous islands, we have this pretty image during this type of situation. So also looking at the impact of persistent east quadrant over the Iberian Peninsula, we can see there is a arrow here. You can see there's the east wind, a warm, dry east wind over the Iberian Peninsula, usually affecting Portugal, where the air mass eats over the inner peninsula and reaches the near shore over the west coast of Portugal. So that is mainly the reason why we have forecasted the 35-36 degrees for today here in Lisbon. So we have some yellow warnings for maximum temperature in several places, mainly in the littoral, near the shore, because usually the east winds don't arrive to the east shore, and as we have at least 2 consecutive days of maximum temperature over the limits for each place, we have a yellow warning in some places here in Portugal. So the prediction for the next days also, it looks to be a heat wave if it's confirmed by the observations. The forecast is forecasting a heat wave, so at least 6 consecutive days of maximum temperatures, 5 degrees above the mean temperature maximum of each of these locals. So it's almost every stations where we have this heat wave calculation are predicted for a heat wave in the next day, so late May, early June. We have a similar situation through 11 and 15 of May. It was just short of a heat wave, only had 5 consecutive days of maximum temperature over the limit. So I don't know if you can see here, but we have maximum temperatures as high as 37, 38 in the middle of May. So that makes us wonder how the summer will be. And then the situation was similar with a high pressure over the north of Portugal and a low over the north of Africa, mainly Morocco. Another impact with these east quadrant waves are the southeast waves in the south coast of Portugal. So here we have a yellow warning also already issued for this for the coast of southern Portugal, because we are expecting and already observing the 2-meter southeast waves, and to arrive to the southeast waves, we need wind speed, which is being generated by this gradient of these two, of this low and this high. We need a fetch, so we need a distance over which the wind blows over the ocean and a constant direction, and we have a time period. And we know that changes in wind speed easily affect wave height. So once the wind speed weakens or the direction of the wind starts to change, the waves will stop increasing. But the Cadiz Gulf, so it's here, the Gulf of Cadiz, provides in certain synoptic situations, as this one, a wind that has a constant propriety needed for the wave growth. Let me just needed for the wave growth, and usually allowing for a good forecast for southeast waves on the southern coast of Portugal. So, and as I said, the wind speed is generated by the strong pressure gradient due to the high pressure over the Biscay Bay and the low pressure over Morocco, and also aided by the geographic feature of the Cadiz Strait. So the time period expected for the winds to maintain this quadrant is approximately 48 hours. We have here the significant wave height on the top of the chart. And here we already have 2-meter waves prediction. Here you can see the wind is blowing from east-west, and we can see also the maximum wind gust and mean wind and the wave direction. It has a change, a drastic change, so it passes from southwest to southeast very rapidly. And here you can see the model, the our own model predicting wind gusts over 90 kilometers per hour near the strait. So all of that is influencing the waves over southern Portugal. I'll do a small introduction to JSON3. And this is the JSON3 measures sea surface height, wind speed, and significant wave height, which we are looking after a little bit closer. And this primary instrument is the radar altimeter. This JSON3 links up to other altimeter missions, namely JSON2, which we already used in some weather briefings, and with other altimeters, it determines a bias between them and adjusts against the data of JSON3. So it's expected to improve the accuracy of that observation. And the altimeter determines the distance from the satellite to Earth's surface by measuring the time it takes a radar pulse to travel from the satellite to the surface and back. And so it can produce a very accurate measurement. So mainly the mainly key features for JSON3 are the measurements from ocean topography. It's expected to help improve monthly forecasts, namely heat waves and some heavy rainfall, sustained heavy rainfall, and also to improve seasonal forecasts as cold winter and hot summers. This is mainly due to the sustained influence of the sun of the ocean on the atmosphere. So, and here I used the early situation also associated with that heat wave that I showed before, and we can see here here the passages from the JSON3. And this one, which is very important in this situation, because we could compare it to the model. Here we have the model from the ECMWF, the wave model, and you could compare the data from the model with the data from the JSON3. So here I zoomed this part here because it's the mainly part that's where we focus for this situation of 13th of May, and we could see that at red it's the ECMWF wave model, and the blue dots are the JSON tree data observation. It can be here a slight difference in time, so sometimes we can compare that observation of the JSON with the same data of the model, but I think it correlated really well, and we end up having also some southeast waves in the 13th of May. So this is the end. I thank you all for listening to me, and let's see if we have some questions.